Our Earth is 71% water. Most of this is in the ocean. What would happen if our oceans weren't filled with water, but were rather filled with Cornell Chocolate Milk? The surface temperature of the Earth would definitely change. That's because the albedo of chocolate milk is different from the albedo of water. And albedo is the percentage of incoming solar radiation that's reflected by a surface. We can model the Earth with a two-layer energy balance, and this will show us what the exact temperature of the surface of the Earth could be on our chocolate milk world. We can also use this new information to figure out the energy fluxes of the oceans themselves.
The overall energy balance of the Earth is dependent on the albedo of the planet. Chocolate milk has a different albedo than the ocean, so we need to calculate a new value for the albedo of the planet. We don't have fancy instruments to measure the albedo of a surface, but we can estimate the albedo using a camera and a computer. The albedo is the amount of light reflected by a surface. Pictures capture and display the light reflected off surfaces. Therefore, we can use a picture of chocolate milk and a reference surface with a known albedo, in this case paper, to determine how much light is reflected. First, we poured chocolate milk into a clear container so as much of the reflected light as possible is reflected by the chocolate milk. Then, we took a picture in a well-lit room of the chocolate milk and paper in the frame. Using a computer program, we took a histogram reflectance of both surfaces. The ratio between these reflectances is also the ratio between the albedos of the surfaces. Given that the albedo of paper is 0.65, the albedo of chocolate milk was calculated as 0.39. In order to calculate the albedo of the planet, we needed an estimate of the albedo of Earth's landmass. The planet is comprised of 71% ocean and 29% land. We know that the albedo of a cloudless Earth is 0.15, so we calculated the albedo of land using the weighted average. We used the same weighted average, this time using the albedo of chocolate milk to calculate the albedo of a new cloudless planet. This albedo is 0.36. Assuming that clouds increase the albedo by an extra 15%, the albedo of our planet using a chocolate milk ocean is 0.51.
Here's our two-layer energy balance for the atmosphere. ISR stands for the total incoming solar radiation from the sun. At each layer, some energy is absorbed, so only a fraction of the total incoming solar radiation is passed through to the next layer. A2 is the fraction of the incoming solar radiation that passes through layer 2 and reaches layer 1 of the atmosphere. A1 is the fraction of the incoming solar radiation that passes through layer 1 and reaches the Earth's surface. R is the albedo, or the fraction of the incoming solar radiation that is reflected back into space. The Earth re-emits the energy as outgoing long-wave radiation according to the Stefan-Boltzmann equation. Sigma T to the fourth is equal to the energy. In addition to this, a fraction of the long-wave radiation escapes through each layer, which is defined in this diagram as W. We calculated the overall energy balance and the energy balance at each layer by setting the net incoming radiation equal to the net outgoing radiation. We solved this system of 4 equations to find the temperatures of each layer. When we used this model assuming a water ocean similar to our own Earth's, we calculated the surface temperature of the Earth to be about 94 degrees Fahrenheit. This is a little warmer than the observed temperature, as our model did not include latent and sensible heat fluxes and the resulting convection processes. The increased albedo of our Cornell Chocolate Milk ocean caused the surface temperature to drop to 39 degrees Fahrenheit.
In order to understand how the climate of our chocolate milk world will behave, we want to understand the vertical and horizontal energy fluxes. We can quantify these values by doing a surface energy balance. Here is a schematic of the surface energy balance around a control volume of land or ocean. If we do an energy balance around this system, we derive the following equation. Rs is the net radiative flux of energy into the surface. The net radiative flux is the sum of the upward and downward shortwave and longwave radiative fluxes, and it depends on the surface's temperature, albedo, and emissivity, which is a measure of how effective a surface can emit longwave radiation. Le is the latent heat flux from the surface to the atmosphere. This heat flux depends on the latent heat of vaporization of water vapor, or in our case, the heat of vaporization of chocolate milk. Sensible heat, or SH, is a sensible heat flux from the surface to the atmosphere, which is a flux of energy conducted from the surface to the atmosphere. Delta FeO is the horizontal energy flux out of the control volume. For our analysis, we assumed we were at steady state, so there was no storage of energy in the land or ocean. As a result, the horizontal energy flux is equal to the following. dsdt is the storage of energy in the land or ocean. We modeled the surface energy budget for our current Earth's ocean based on the surface energy balance in figure 418 in the textbook. We use sinusoidal functions to model the net radiative heat, evaporative cooling, and sensible cooling fluxes. We calculated the horizontal energy flux using our steady-state energy balance. On the y-axis, we have the energy flux in watt per meter squared, and on the x-axis, we have latitude. As you can see, the net radiative heat peaks at the equator, along with many of the other fluxes. We used our modeled heat fluxes for our current oceans to estimate the heat fluxes for our chocolate milk ocean. We changed the amplitude of the net radiative heat flux to account for the change in the surface's temperature and albedo based on our calculations. We assumed the emissivity of water and chocolate milk were the same. We scaled the amplitude of the latent heat flux to account for the change in the saturation-specific humidity with a change in surface temperature. Specific humidity is a function of temperature, and the latent heat of vaporization of milk relative to water is approximately the same, so we neglected this value. We assumed the composition of the atmosphere did not change, so the sensible heat flux was the same. We compared the heat fluxes for our two oceans, and you can see how the energy fluxes decreased for the chocolate milk ocean. The radiative heat and latent heat fluxes decreased significantly from one ocean to the next. However, the horizontal heat transport flux remained relatively the same.